This video illustrates how dynamic networks can be visualized with Cubix and the matrix cube. A matrix cube represents a dynamic network as a space-time cube based on adjacency matrices, one for every time step in the network. Vertices in the network are represented as the rows and columns. Here we explore a collaboration network, where vertices are authors and edges are publications. The size of cells indicates the number of publications, and each cell stands for a collaboration between two authors on a given year. To obtain a better impression of time, we switch to an alternative color encoding, coloring cells according to their position in time from blue to orange. Cubix provides several predefined views on the cube. This small cubelet widget can be used to navigate between them. If we click on the right face, the matrix cube gets rotated so that we attain a picture of the network's topology in the time projection view. Cells get superimposed, but can be revealed by changing their transparency. We can see from the violet cells that edge weight has decreased over time, while the edge weight of orange cells has increased. If we rotate slices by a right-click on the slice label, we can observe the evolution of edge weight in detail. In order to emphasize the network's topology, we can make all cells the same size. We switch back to a weight encoding. As cells are still transparent, we see the accumulated edge weight. Disabling any color encoding turns all cells gray, and we now see the number of years of collaboration. We continue our overview of the data by having a look at the general temporal evolution of the network. We rotate the cube to the vertex projection view and clearly see a trend towards more collaborations, except in 2008. We now want to compare time slices and see why 2008 was different. We switch back to the time projection view and can browse through all time slices by hovering these labels. While this can work nicely for small networks and when comparing individual time slices, having all time slices at a glance allows us to quickly spot three phases in the evolution of this network: an initial growing phase, a restructuring phase, and a relatively stable phase in the end. Similar to time slices, we lay out all vertex slices and can compare individual activity patterns. Here we see the delay dataset, also showing baselines between antennas. Since dark blue cells are much more distributed, we filter out low-weight cells using the edge weight slider. The histogram indicates the distribution of edge weight. He first switches to the vertex projection view. However, as all vertex slices are superimposed, this view does not make it easy to spot specific baselines. He realizes this and decides to switch to time projection view. Some rows and columns stand out, indicating possible antenna-based problems. From there, the astronomer wants to get an overview of what antennas feature higher variability. For some antennas, roughly half of the baselines have much larger delays than the other half. The astronomer switches back to stacked vertex slices to quickly brush them through in more detail. There is no clear explanation for this observation that requires further investigation by looking at additional data not available here. Here we analyze signal patterns between regions of the brain. Our expert is interested in identifying the time steps that feature a high activity level overall, connectivity patterns that reoccur over time, and what regions are active at specific moments. The red cells show when a region sends. Blue cells show when a region receives. Size of cells is mapped to signal strength. We can already see the symmetry between red and blue cells. We can also see that some of the 150 time steps stand out as much more dense, that is, they show higher activity between regions. By observing all time slices at once, we do not find much recurring connectivity patterns among the highly active time steps, but realize that beyond symmetry, one pattern appears consistently across all slices that feature a high level of activity. 2 or 3 regions receive from exactly 4 other regions, blue cells in the same row. This network is complete, containing 9,600 cells, and we remove the cells with the smallest signals by keeping only the strongest signals. Seen from the side, the highly active time steps are clearly visible. We realize that one region seems to be more involved in sending and receiving signals. We rotate some of the time slices in place in order to see if this region is one of the 2 most active. We thus bound the set of visible time steps and switch to the time projection view. In fact, we can see that, amongst those that feature high signals, region 4 is sending and receiving more often than others. We now move the time range slider in order to travel through time and observe other time ranges. We notice that region 0 is also very active. We finally take a closer look across regions in the vertex small multiple view. Here we see that region 0 is indeed more active in certain time steps, together with region 4, and that region 4 seems to send far more signals, red cells, than it receives.